Oxidation numbers are very straightforward. Remember, there's only one reason we do it, and it's to literally keep track of what's gained and lost. And that's it. We just need to know what electrons are gained and what electrons are lost. And so we assign oxidation numbers strictly for that purpose. So the rules that we want are very basic. When you assign oxidation numbers, there's a few things you do remember. First, all elements in their elemental form. Now, elemental form could be metals that are solids. It could be gases, so oxygen. If you see oxygen gas, that's its elemental form. If we see any kind of solid metal, etc., those are the elemental form. They automatically get an oxidation number of 0. Any monatomic ions, so what we're typically used to seeing on the periodic table, those will always receive whatever their charge is. So we talked about that probably in chemistry before, and you talked about the basic rules associated with column 1 being +1, column 2 being +2, and so on. And so whatever the charge is of a monatomic ion, that's what it is. So even if we're talking about the transition metals here, if they're a monatomic ion, that's their oxidation number. When we go then to nonmetals, we start seeing some, I guess you might say some, it's not always the same number. It depends on what's going on. So here, we always typically think of oxygen as being -2, which it usually is, except when it's what's known as the peroxide ion. And we see peroxide in things like hydrogen peroxide. You'll see peroxides happen a lot with different organic compounds. And this is neutral, and it has a charge of -1. Hydrogen changes depending on what it's bonded with, because again, hydrogen has that single electron. We have typically hydrogen 1, we have 1 proton. Okay, so hydrogen 1 is typically 1, 1, and then we either have a -1 because it gained it, because it can accept 1, or it's a +1 because it gave it away. So it depends on what it's combining with. With a metal, it's always negative because it will typically have a higher electronegativity than most metals, and it's literally usually +1 with nonmetals because it typically has the lower electronegativity than nonmetals. Now the halogens are where we see a lot of fun, and have a lot of fun with the halogens, because primarily it depends on their ability to form oxyanions. Fluorine, no matter what, will be -1. It doesn't form oxyanions. But chlorine and iodine and bromine, they can, and that's where you get the chlorates and the bromates and the iodates and the iodites and the bromites and the chlorites, etc. So that's when you will see positive oxidation numbers with them. And again, it's just a matter of counting. So for example, when we look at hypochlorite, the overall ion has a charge of -1. Well, we just established that oxygen should have a charge of -2. So that means my oxygen's my -2. Well, what charge does chlorine have to have for this statement to be true? Well, chlorine has to have a charge of +1. And by the same token, chlorite, ClO2, the chlorine can't be +1 still because I have more oxygens. So my oxygen is 2 times -2, which gives me an overall -4. That still has to equal my -1, so chlorine actually has to become +3 now. And so that's why we do oxidation numbers, simply to track what might happen, because if this becomes reduced, meaning the chlorine gains electrons, we will notice it by the oxidation numbers. One last thing, sum of your oxidation numbers in a neutral compound is 0. The sum in a polyatomic ion is the charge on the ion, and that's what we've been discussing here.